Hello everyone, in this section I will share with you a new topic, that is the filter design. This topic I will share with you the Finite Impulse Response FIR filter. In fact, there are two types of the filter, that is the FIR filter and IIR filter. FIR filter refers to Finite Impulse Response and IIR refers to the Infinite Impulse Response. Before this, let's compare what is the difference between the FIR and IIR filter. Okay, this is the criteria of the comparison. Okay, for the IIR filter, in terms of phase, IIR filter is difficult to control the phase, whereas FIR is easily to be designed to be linear phase. For the filter order, IIR has the lower filter order and FIR has the higher filter order. In terms of stability, IIR can be unstable, whereas FIR is always stable. In terms of design, IIR design using closed-form design formula and feasible by manual computation, whereas FIR is a closed-form design formula does not exist and need iteration, and it is more suitable using the computer. IIR has less number of elements, whereas FIR has more number of elements. And in terms of implementation, IIR should be more difficult and FIR filter is more easier. For the cost, of course, IIR is cheaper, but FIR is more expensive. However, the IIR execution time is faster than the FIR execution time. Now let's go to the FIR filter design. FIR filter involves a selection of the finite sequence that best represents the impulse response of an ideal filter. FIR filter always stable and therefore is more important because FIR filter able to perfectly linear phase. This means that it's free from the phase distortion. However, FIR filter require a higher order of the filter design than the IIR filter. Or somehow we need to go to the higher length or greater length to ensure the linear phase. There are three commonly used methods, that is the window-based design using the impulse response of the ideal filters, or the frequency sampling and the iterative design based on the optimal constraint. For the window-based design, it starts by selecting the impulse response Hn as the symmetrically truncated version of the impulse response Hn of an ideal filter with the frequency response Hf. And the normalized cutoff frequency Fc, okay, for the impulse response of an ideal low-pass filter can be calculated through this formula, Hn equal to 2Fc sin 2nFc. And the symmetric truncation is the Hn equal to 2Fc sin 2nFc. Then the n is equal to even and not integer. For the characteristic of a window function, this graph shows the magnitude spectrum of a typical window and the amplitude response of symmetric finite duration of the windows. This is the main loops, and this is the decaying side loops. Can be entirely positive or alternate. It means that it's a positive, negative, positive, negative. The first side loop is referred to the peak side loop, okay, PSL, and it is in a unit of decibels. And the decay rate ds is in dB per decade. The x-axis is in the frequency base. So the main loop with the width of the Wm. And this table shows the windows commonly used in FIR filter design. It has Boca windows, Riemann, Bartlett, Von Heming, Redman, and Kaiser window. And for the right hand side is the expression for the Wn, this one, for the particular window here. This figure shows the commonly used discrete time Fourier transform windows and their spectra. So this is the rectangular window with n equal to 21, and this is the magnitude spectrum in dB. Whereas this one is a one-hand window with n equal to 21, is equal to 21 point. Okay, and this is the magnitude spectrum. Whereas the Hamming window, n equal to 21 also, so it is from minus 10 to 10 with the origin is equal to 0. And this is the respective magnitude spectrum. Whereas this one is the Blackman window with the same n equal to 21 too. And this is the magnitude spectrum. Okay, it's slightly different from the previous. Previous is this one. Okay, this is the Von Hand and the Hamming. And whereas this one is the Blackman, and last one is the Kaiser window. Okay, Kaiser window with beta equal to 2.6. And this is the magnitude spectrum. It can be seen that the main lobe is bigger as compared to the side lobe. Whereas for the Hamming, the side lobe is nearly almost the same magnitude. And for the Von Hand is decrease slowly. Whereas for the Kaiser and Blackman, it declares quickly, the side lobe declares quickly, okay, and small. This slide shows the example of the calculation, okay, based on the table given. For example, this is the window for the cosine, and the expression for the Wm is this one, cos pi n over n minus 1. And then for the n from minus 0.5 n minus 1 to positive 0.5 n minus 1. So if you look at this, let's say n is equal to 21 as in the figure given, 21 minus 1, you got 20 times with the minus 0.5, so you got 10. So from minus 10 to 10. For the window cosine, so this is the the expression of the Wn. And then you substitute the value, the n is when n equal to 0, what is the value? And when n equal to 1, what is the value? You substitute in here. Then make sure the pi here is in the radian. Here is another example for the Von Hand or Hamming. The difference is just the expression of the Wn. Okay, the expression for the Wn, and you substitute in the n here with 0, 1, 2, 3 up to the value that you want. And this one shows the spectrum characteristic of the window function. For each window, you have a different GP. This GP refers to the peak gain of the main lobes, and GP over GS. Okay, GP over and GS. GS is referred to the peak side lobe gain. Okay, and then this one is the ASL. ASL is referred to the side lobe attenuation for in dB. And Wm is the half width of the main lobe. Because it's a symmetric, so we only add positive, so it's the half width of the main lobe. Like the graph that you see here is the half width only. And then also W6, W3, and DS. And this is referred to here. This means you have 0.07p is at this level. Okay, is the W3, and then 0.5p is W6, and the peak of the main side lobe here, okay, is this one, and Wm is the main lobe peak. And so this is the formula to find the GP over GS, Wm, and Ws. From the graph, we can say that the one-hand window improves the high-frequency decay at the expense of a large peak side loop level, and the heavy window minimizes the side loop level at the expense of the slower high-frequency decay, whereas the Kaiser window has a variable parameter beta that controls the peak side loop level. Whereas the Kaiser window best approximates such an optimal window in the discrete domain. Window in filter design is always symmetric. So symmetric windowing of the impulse response of the ideal filter is accomplished by the windows that are themselves symmetric. If you look at this graph, this is the example for the Bartlett window with n equal to 13 and n equal to 10. The difference is that if you have the even number n equal to 10 means that you don't have the origin, because it is n equal to 10 and you have the 9 interval. And then if you have the odd number where n equal to 13, so you have the extra one is the peak. This peak is the origin. So there's a difference between the odd and even value of n. N-point FIR window use the n-1 interval to generate n samples, including the both n samples. Okay, once selected, the window sequence must be symmetrically positioned with respect to the symmetric impulse response sequence. So windowing is simply a point-wise multiplication of two sequences. This like this. Okay, windowing hash w is equal to the hash n and multiply with the wn. So this is the point-wise multiplication. This one also equal to the hash n is the 2fc sin 2nfc multiplied with the wn. And this n should be in between minus 0.5 and minus 1 to positive 0.5 multiplied with n minus 1. Therefore, it is said that for even n, the index n is not an integer and it requires non-integer delay to produce a causal sequence. Now let's look at the example. Given a low-pass filter with a cutoff frequency of 5 kHz and a sampling frequency of 20 kHz, using a Bartlett window of length n equal to 9, determine hash n, wn, and hash wn. Hence, calculate the low-pass transfer function of the causal sequence hash c if the n samples are included and the n samples are ignored. Then calculate the required delay in a millisecond for both cases. The question given the cutoff frequency equal to 5 kHz, sampling frequency equal to 20 kHz, and design using a Bartlett window with n equal to 9. So first of all, you need to find the digital frequency. That is Fc equal to cutoff frequency divided by S, that is 5K divided by 20K. So this is equal to 0.25 Hz. So second, symmetric truncation impulse response. Okay, so hash n equal to 2fc sin 2nfc. So this is the formula. And we substitute in the fc, that is 0.25. And then next, 0.2 times 0.25, that is 0.5 sin 0.5n. So this is equivalent to 0.5 sine 0.5 pi n divided by 0.5 pi n. So from table, Bartlett window give the wn equal to 1 minus 2 modulus n divided by n minus 1. So this is for negative 0.5, n minus 1 to 0.5, n minus 1. So this is roughly the n is equal to 9. So 9 minus 1 is 8. 8 times negative 0.5, so you get negative 4. Negative 4 to 4. And now we can, based on the Hn and Wn formula, to find the value. Okay, find the value of both. So first of all, we can draw a table. So from here, n we have the 9, right? N equal to 9. This means is from negative 4 to 4. So we can put the n value from negative 4 to 4. 1, 2, 3, and 4. Okay, the Hn, okay, based on the value, based on the formula of the Hn, so you substitute in the n here with negative 4, negative 3, negative 2 up to 4. And then I have calculated it, so I get 0, negative 0.1061. This is also 0, 0.3183. And then this one I get 0.5, and this one I get 0.3183. This one I get 0, this one I get negative 0.1061. This one I get 0. And the Wn also I use this formula. I get 0, 0.25, 0.5, 0.75, 1, 0.75, 0.5, 0.25, and 0. So this, now here is A times B. After you find the Hn, Wn, now you find the Hwn. So Hwn, do you still remember? Just now the slide said that the Hwn actually is the pointwise of the Hn and the Wn. So you multiply. This one multiply with this one, you get 0. This one multiply with this one, you get negative 0.0265. This one you get 0. And this one you get 0.2387. This one you get 0.5. This one you get 0.2387. This one you get 0. This one you get negative 0.20265. And this one you get 0 also. If you notice here, where n equal to 9, that is the odd number, it has the origin. So this is the origin. And the value here actually is a symmetric at the origin here. Okay, so it means that the right hand side value is same as the left hand side value. So that's why it says the symmetric truncation. The question asks you to find the transfer function of the causal sequence if the n samples are included. The n samples are included and is for causal. What is for the causal? So for the causal, this means that, okay, here is the 0 and you have the value here. Okay, you have the value after the 0. So it's called causal system. So what is the n sample? If the what if the n sample are included? So a causal filter require a delay of 4 samples, because if you look at here, if the causal system means that it starts with 0, okay, so we require a delay for how many samples? 1, 2, 3, 4. But if the n sample is included, so it means that this is the last sample. So do we have the 1, 2, 3, 4? So a delay of 4 samples. So HWN minus 4. So this equivalent to, okay, this means that you move the origin to here. Okay, and the value are the same. So I write down here the value. So 0, negative 0.0265. And what about the transfer function? The transfer function, I can write it by HCZ equal to 0 minus 0.026 z power minus 1, okay, plus 0.2387. Okay, so this one I can silence, so I read this one. So this is z number 3 plus 0.5 z power minus 4 plus 0.2387 z power of minus 5 minus 0.0265 z power minus 7. So this one we also can silence. So this is the transfer function. And then the question also requests you to find the delay, right? Find the delay. So S is equal to 20 kilohertz. So TS is equal to 1 over S, which is equal to 0.05 millisecond. So 4 sample delay. So just now when the N sample are included, so you have 4 samples of delay, which means that is 4 times with 0.05, so you get 0.2 millisecond. And then the second question is the N sample are ignored. Okay, if the N sample are ignored, means that we don't want to count this one. Okay, so we only have the delay for the 3 samples only. So HW N minus 3 is straightforward. They're not to exclude the 0 value. So we start from here. And for the transfer function, it's the same like a previous. It's the origin. Plus with this one can silent. So we start with this one. So you have 0.2387 z power minus 2 plus 0.5 z power minus 3 plus 0.2387 z power minus 4 minus 0.0265 z power minus 6. And 3 sample delays. So 3 samples of delay is equal to 3 times 0.05. We obtain 0.15 millisecond. Now let's look at the example. Given a low-pass filter with the sampling frequency of 20 Hz and XDFTK equal to 0, 7, negative 2, 1, negative 3J, 5, 7 plus 6J, 8J, 3 plus 4J, and 5. And origin is at the first value. Using the Von-Hand window, find the modulation frequency Fm, the magnitude of the XDFTK, cutoff frequency, jitter frequency, and the HNWN and the HWN. Now, this is the given information. And first of all, we need to find the frequency, modulation frequency Fm. So based on the sampling theorems, S more than equal to 2 Fm. So we need to find this Fm. And S is equal to 20 Hz. So Fm is equal to S over 2, which is equal to 20 over 2. And this is equal approximately 10 Hz. So this means that the frequency components that should exist are between 0 to 10 Hz. And then we also can find for the T equal to 1 over S, which is equal to 1 over 20. And this is equivalent to 0.05 seconds. Question B, we need to find the magnitude of the XDFTK. So magnitude of the XDFTK is equal to 2 over n, and then real number of the XDFTK plus with imaginary part of the XDFT. and then square root, and then square and square root. So this is the formula. The n here is referred to the number, the number of a sequence. Okay, for example, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n is equal to 10. Okay, based on the question. So we need to find the magnitude of the XDFT. So real XDFT, which means that if you have this one, for example, this is a complex number. So real number is 3. So 3 square plus imaginary part number, so 4 square and square root. And then multiply with 2 divided by 10, the n value. So I have calculated for k equal to 0, and the magnitude of XDFT 0 is equal to 0, because based on the XDFT value. So when k equal to 1, the magnitude of the XDFT 1 is equal to, okay, so now you have the 7. So 7 square plus, you don't have the imaginary, so plus 0 square and square root, multiply with 2 and divide by 10. So I get 1.74. And when k equal to 2, magnitude XDFT2. So it's the same method. So negative 2 square root, square and square root, and then multiply with 2 and divide by n. So divide by 10. So that is equal to 0.4. So when k equal to 3, I have the magnitude of the XDFT3 equal to 0.2. And when k equal to 4, the magnitude XDFT4 equal to 0.6. And when k equal to 5, the magnitude of XDFT5 is equal to 1. Okay. And when k equal to 6, the magnitude of the XDFT6 is equal to 1.84. And when k equal to 7, the magnitude of the XDFT7 is equal to 1.6. And k equal to 8, the magnitude of the XDFT8 is equal to 1. And then k equal to 9, magnitude XDFT9 equal to 1. So this is the magnitude of XDFT from 0 to 10. Okay. So from the calculation, which XDFT k value give the highest magnitude? Let's check. Okay, this one and this one. Okay. So this means that from the calculation, it's found that the XDFT6 and XDFT7 give the highest magnitude, which means that only f equal to 6 Hz and f equal to 7 Hz. So f equal to 6 Hz is the highest frequency component. Okay, this one is the highest. So thus our low pass filter is designed to eliminate the f equal to 6 Hz. So we want to find the FC, the cutoff frequency. FC equal to F high plus F low plus F high divided by 2. So 6 Hz plus 7 Hz divided by 2, which is equal to 6.5 Hz. Okay, which is equal to 6.5 Hz of the cutoff frequency. And next we want to find the digital frequency. Digital frequency of the low pass filter, FC, is equal to FC over S, which is 6.5 divided by 20 Hz. This is equal to 0.325 Hz. Okay. And next question, we want to find the Hn. Hn is still remember the formula, that is the 2 FC sin 2n FC. Okay, so 2 FC is 0.325 sin 3 times n times with 0.325. So this is equal to 0.65 sin 0.65n. So we can change the sin to sine. So 0.65 sine 0.65 pi n divided by 0.65 pi n. So from the table, one hand give the 0.5 plus 0.5 cos 2 pi n over n minus 1. And it is from 0.5 n minus 1 less than n and less than 0.5 n minus 1 too. And this equivalent to 0.5 plus 0.5 cos 2 pi n over 9. And for the range of 0.5 times with 9, and then to 0.5 times with 9. So this is from minus 4.5 to 4.5. Okay, and then we draw a table. So okay, we draw a table. So this is for the n. This is the hash n. And then we have wn. And then we have the hash wn. Okay, so the range is from minus 4.5 to 4.5. Okay, using this one. So that means that the n is from negative 4.5 here. And then we have negative 3.5. We have negative 2.5. And then negative 1.5. (0.5) and then positive 0.5. So this is the same. So 1.5, 2.5, 3.5, and 4.5. Okay, so for the hash n, we have the formula from here, hash n. So you have 0.65 sine 0.65 pi n divided by 0.65 pi n. So the n here you substitute with the value here. Okay, for example, you start with the negative 4.5 first. You substitute in the n, then you get 0.0165, and then for negative 3.5, I get negative 0.0691. And then for negative 2.5, I get negative 0.1176. For negative 1.5, I get 0.0166. For negative 0.5, I get positive 0.542. It's same to this one. So this value will be the symmetric value to this one. So I get the same value. Okay, and then for the Wn you follow this value, this formula, 0.5 plus 0.5 times with the cos 2 pi n divided by 9. And for this one, I get 0 for the first value. Okay, and then for the hash w, it's just pointwise of the pointwise multiplication of the hash n and wn. So I get here 0. I get here 8.08 milli. Okay, so this value is the of symmetric value. Okay, so this is how we get the HNWN and the HWN. That's all for this question. Hope you can understand. Thank you for watching.